Yeah, hello. So, am I audible?
Yes, you're audible.
Okay. Just a second. So, when is the week 3 assignment date? Just check.
It's due tomorrow.
Okay, okay. So, do you have any doubts like till week 3, anything or assignments or anything? Did you get the op-amp question, by the way?
Not really. I actually got it wrong.
Oh, okay. But you got the idea, right? How to do it?
Yes, I got the idea. Yes.
Okay. So, any other doubt till week 3?
None so far. I'll definitely ask it in the forum if I get
Oh,
it.
okay, cool, cool. So okay, maybe today's session, if no one is there, maybe we can wind up earlier. So yeah, so we'll look at all the week 3 is actually pretty easy compared to week 2 because it's all just decompositions which you would have already done in your basic math course. So yeah, firstly, okay, okay, is it recording? Just a second. Yes, it's recording. Okay, so yeah, we'll begin first with change of basis. Change of basis. So okay, so why is there even a concept of change of basis? Because bases are not unique. So if you know maybe today we'll look at more geometric point of view than just linear algebra. So let's say you have a you have a coordinate system x1 x2. This is in fact your standard basis 1 0 0 1. This is your standard basis. Yeah, so this is b1, I'll call it. Okay, now let's say you are in a moving object, okay, which rotates. Okay, let's say you have a mobile robot or something which can rotate, okay, which is at this origin. It can translate also, but we'll just look at rotations. So now if you want to send something, so this will be my uh, earth fixed frame, or you know it's fixed to the it's a fixed reference frame, it doesn't move. And let's say this is my other so I'll call it y1 y2. I'll call it b2 is equal to so this will be 1 by root 2 1 by root 2 and minus 1 by root 2 1 by root 2, correct. Basically it's rotated 45 degrees. Okay, so yeah, so something like this. So now if you want to make a measurement of an object over here, okay, let's say there is some object, okay, with respect to this. So always your measurements will be with respect to your body fixed frame, right? Any robot, any object, any vehicle, anything, it will be with respect to your body fixed frame. So you will make a measurement with respect to this. Okay, so you have a coordinate system here, y1 y2. Okay, you will get a maybe one sec, I'll just copy paste this. Okay, never mind. Yeah, so b1 x2. Okay, yeah, yeah, sorry. So yeah, this is my, so if there is an object here, now the coordinate is y1 y2. I want to know what the you know the how the object is with respect to x1 x2. Okay, So what do? I know that wherever the object is, its absolute position is the same. Okay, absolute position in the sense B1 x equal to B2 y, correct. So yeah, so if you write like this, then you can write x is equal to B1 inverse B2 times y. Okay, so this is my change of coordinates matrix. So I know there is this inverse x is because it's a basis vector, right? Basis vectors are linearly independent. So in this case, it will be B1 inverse is nothing but identity, B2 is 1 by root 2, 1 by root 2 minus 1 by root 2 and 1 by root 2. In fact, this is a rotation matrix. So if I think you are from aerospace, right? So you would know what rotation matrices are. So
Yes.
yeah, so this in fact is the rotation matrix in this case, because it the reference frame itself is rotated about 45 degrees in this case. Okay, so yeah, so that's exactly change of basis, nothing. So I'll give an example which you would rarely come across as an aerospace engineer or in mechanical systems. I'll take a question. So let's take B1 is equal to 1 t square, and my vector space is set of all polynomials with degree less than or equal to 2. So you can check if this is actually a vector space. If you add two vectors in this space, it will still be a polynomial of degree less than or equal to 2. Any scalar multiple will be again a polynomial with degree less than 2. Okay, so yeah, so that's there. Then you have a vector space here. Now I am choosing one basis as 1 t square, another basis as 1 plus t, 1 plus t square. You can in fact prove that this is actually a valid basis, they are linearly independent. Okay, you can actually prove that. So I want to write the change of coordinates now. Okay, so how do I write this? So first I write B1 as a the transformation matrix times B2. Okay, so the transformation matrix in this case 1 t. So I need to write these coordinates in terms of this coordinates. Okay, so what I will do is, this is nothing but 1 times 1 plus 0 times 1 plus t plus 0 times 1 plus t square, correct. And in the second case, what is this? This is minus 1 times 1 plus 1 times 1 plus t plus 0 times 1 plus t square. And the third one is 0 times 1 plus minus 1 times 1 plus t plus 1 times 1 plus t square. Okay. Now I need to write this in a matrix form. So that will be 1. So it's a you are taking from one to the other. So it's there will be a transpose there. So 1 0 0 1 0 0 minus 1 1 0. I'll show you an example why if it's correct or not. 1. Okay. This is my change of basis matrix. Okay. Now let's take a vector. Okay, let's take a vector in B1 basis. Okay, whose coordinates are given with respect to B1. Okay, so I'll call it V1 equal to 1 plus 5t plus 2t square. Okay, this is my vector. It's a vector space. So all the points in that vector space is a polynomial of degree less than or equal to 2. Okay, so this is my vector. So what is my how do I write this as a this is nothing but your I cap, j cap, k cap in if you want to look at it that way. So this is nothing but 1 5 2. Okay, that's correct. So this is actually my vector. So this is my polynomial. You can write it like this as a coordinate form. Okay. So now I want to write it in the other basis. So what should I do? Just multiply it, right? So I'll multiply that. So this will be nothing but I'll take it V2 is 1 minus 1 0 0 1 minus 1 0 0 1 times 1, 5, 2. So that will be equal to okay, minus 4, 0, 5 minus 2, 3, 2. Okay. Now what are these? These are coordinates, right? So these are coordinates. So how do I write the basis? Minus 4 times 1 plus 3 times 1 plus t plus 2 times 1 plus t square. So that is nothing but minus 4 plus 3 is minus 1 plus 2 is 1 plus what is the coefficient of t? 3 plus 2 is 5t, okay, and finally plus 2t square. So you see, in fact it is the same vector, okay. So in whichever basis you take, it is the same vector. So yeah, so this is just this is the basic, you know, thing of coordinate change. Okay, so now you can do it in any. So why do you need to do a coordinate change? That is the first thing. So what the thing is, let's say you have some dynamical system. Okay, so let's say you have a dynamical system, x dot equal to ax. Sometimes in some coordinate change, it is very easy to analyze the system. Let's say in some coordinate change, it is a diagonal system. We will see how you can in the eigenvalue decomposition, we will see how you get that. So in some coordinate change, you can actually write the system as a diagonal form. So why? So what is the benefit of, you know, having a diagonal form? It's because you can now decouple the system, decouple all the states. So z1 dot is some lambda 1 z1, z2 dot is equal to some lambda 2 z2, etc. So it's decoupled now. So what does this imply? Z1 of t is e raised to, this you would have done, right, in your, this is basically a solution of ODE, lambda 1 t, z1 0, etc. Zn of t e raised to lambda n t, Zn of 0. So this is so you would have heard of in vibrations and all, you decompose the dynamics into its modal components, into its different modes, okay. So it's the same thing. So change of coordinates actually helps you in certain cases, okay. So this is why you need change of coordinates. Now let's look at something called similarity transformations. Similarity transformations. Okay. So what are similarity transformation? So since these matrices, in fact, just a second, yeah. So we know that depending on the states you choose, right, in state space, you can choose a position. So let's take a mass spring system, okay, K1, M1, let's add a damping also, okay, that's a mass spring system. So I can choose x1 is equal to x and x2 equal to v, or I can choose x1 equal to v and x2 equal to x, right, it does not matter. So what is my dynamics here? In this case, x1 dot equal to x2, which is first derivative, x2 dot equal to minus k by m x1 minus b by m, b is the damping coefficient, b by m x2, okay. So what is my A matrix? A matrix is 0 1 minus k by m minus b by m. This is my A matrix in this case, correct. In the first week we would have seen that. So, but in this case what is it? So x1 dot is minus k by m x2 minus b by m x1, and x2 dot is nothing but x1, okay. So this is, so what is my A matrix? I will call it A bar. A bar is nothing but minus b by m minus k by m 0 1 0. So but then you know that the system is the same, right? I am dealing with the same system, correct. So all the properties of the system must be the same. So all the properties of this A matrix must be the same as the properties of this A bar matrix, right? So that's, so we can't say that the matrix are same, because they are clearly not the same. These both are not the same. But if you look at their rank, eigenvalues, eigenvectors may not be the same. Eigenvalues, it may be transformed like in a different basis. So eigenvalues, determinant, if the eigenvalues are same, determinant will be same, then your trace will also be the same. Okay, all these are same because these eigenvalues and all and the rank actually tells me the properties of the system, right, the dynamics of the system, how fast it will go, how fast it will converge and things like that. So these are same. Okay, so then, so how do you relate these two matrices? So you can relate these two matrices by P inverse A bar P. There exists a invertible matrix P such that you can write A equal to P inverse A bar B. You can always find that matrix in this case. Okay, so yeah, so that's the idea of similarity transformation and why do you need it. So in control theory, you might come across similarity transformation when you analyze controllability. Okay, controllability, observability, and things like that. So that's where your similarity transformations would come, because it makes things easier in a different coordinate system. Okay, so yeah, so this is the similarity transformation. So now we look at a problem. So what should I, which problem? Okay, so maybe you can do this. I am saying A is similar to B. So I think some notation, some people use A is similar to B like this, some people use with equal to. So yeah, A is similar to B. Now show that A raised to K is similar to B raised to K. So how do you do that? So maybe you can we can do the question together if you. So this is given, show that A raised to K, where K is any positive number, is similar to B raised to K. So how do I start? So any idea? You can unmute and say.
So maybe we can start by finding a model matrix.
Yeah, we don't need to find actually. We can just let's say P inverse BP. Okay.
B, yeah, same thing.
So now I'll just take the power. So which implies A raised to K is nothing but P inverse BP whole raised to K, correct? Which is nothing but P inverse BP multiplied over and over. Okay, P inverse BP. Now all this P inverse P will get cancelled. You will get I identity. This is nothing but B raised to K P. So now you are saying there exists a P such that A raised to K is equal to P inverse B raised to K P, which implies A raised to K is similar to B raised to K. That's it. So you will use this over and over. Let's say in when you have discrete time systems, I'll give you an example where you will use this Ax of K. Okay, what is x of 1 equal to Ax of 0, and if you write like that, you will get x of so what is x of 2 equal to Ax of 1, which is nothing but A square x of 0, correct? So finally you will get x of K is equal to A raised to K x of 0. So if you want to do a similarity transformation on this, you can just do a similarity transformation on this and take the power of that. Okay, it's the same. So that's where you will use this. Excuse me. Yeah. So okay, so that's pretty easy, right? The similarity transformations are pretty straightforward. Finding the model matrix is the difficult part actually. So you have to choose a model matrix correctly. That depends on what sort of transformation you are doing. So we look at some similarity transformations. Okay, so one very important concept in entire control theory, if you look at nonlinear controls, are invariant subspaces. Okay, So what do they signify? So in most control theory, in this course it's all linear, but in non-linear as well you come across these terms called invariant subspaces. Okay. So let's say you have a vector space V and S is a subset of V or subspace of V. Okay, it's a subspace of V. So let's say I draw a vector space V, and then I have a subspace. I'll call, so this is my subspace. Okay, this is S. Okay, so the concept is take any x belonging to V. S. Then if you have a linear transformation, f of x will also belong to S. Okay. So then we can say S is an invariant subspace which is invariant under transformation f of x of V. Okay. So it's a subspace of V which is invariant under this transformation f of x. So you know that linear transformations can be written as f of x equal to some a times x, correct? So what are we saying? So if I, so this is my S. So let's say this is my x. Okay, it tells me I should be on this line all the time, even after multiplying by a. So what does a matrix do to a vector? So matrix does two things. Okay, one is rotation, other one is scaling. Okay, that is what a matrix multiplication does, right? So in this case what we are saying is it shouldn't rotate, it can at most scale. Okay, so by rotate meaning if I multiply this x by a, transform this vector using a matrix A, a linear transformation, it shouldn't go like this, it shouldn't rotate. Okay, it should only scale. So by scale it means you can go here, you can go here, even in negative direction it can scale. Okay, so that depends on the eigenvalue. Okay, so that brings us to the concept of eigenvalues. Okay.
So
Yeah.
basic idea of an invariant subspace is that it's along the same line itself, like
Span, yeah, not just line, it could be a plane also.
okay.
Yeah, so this is for linear systems. Okay.
Okay.
But in general, if I say if I take a set, I can say invariant, invariant set also. It need not be a subspace. It may be a set also. Let's say I am taking a set here. Okay, a set S, and I am saying any point you take and apply a linear transformation, it comes back to the inside the set. Okay, so basically it tells me it's closed under this operation. Closed in the sense, if I am in S, x belongs to S, I apply f. Okay, still f of x must belong to S. That's the idea of invariant subspace. Okay, for linear systems it's very easy because the invariant subspace are the eigenvalues, are the eigenspaces, eigen subspaces. So yeah, so is that clear? Or
Yeah. Actually, this idea of invariant set that makes a bit more sense. So
yeah,
thank you for that.
so in general it's an invariant set, but in a vector space it can be a special case of a subspace. Okay, so a subspace is a set plus some conditions, right? So it's a special case. So this you can view as a set, right? And it has properties that alpha x plus beta y should belong to this S. So yeah, so that's why it's a subspace. Okay, so this eigenvector, eigenvalue, in this case two dimensional space, the invariant space is this line, it's a line. So in 2 dimensions there can be only 3 possibilities. One is R2 itself, second is the 0 origin. Okay, it's possible, right? Any vector you take, you multiply, you get 0. Okay, so it's trivial. And in the first case, if you take any x, you will get x which again belongs to R2. So it's invariant. Okay, and the third case are eigenvalues. vectors, or the span of the eigenvectors, which is my eigenspace. Okay. Why? Because eigenvectors of a matrix, if the matrix acts on an eigenvector, basically A times V, there is no rotation. It only scales the eigenvector. This is just a scaling, right? There is no rotation. Okay, that is the whole point of eigenvectors. The eigenvectors do not rotate, they only scale. Okay, so that is why they are invariant. Again, see, if you see this, so in general it is called an operator. I do not want to go into that, but this is an operator, okay, acting on a vector, or a transformation acting on a vector, and you still are on the span of this, right? What is the span? We said all the combinations which gives rise to this. Okay, so that is the span. So you still remain on the line. Okay. In 3D, you can have you can have R3, you can have the origin, which are trivial. Third is a line, which is an eigenspace, eigenvector, and fourth one is a linear combination, which is a plane. Plane means, so you can have something like this. So you have two eigenvectors, and so which means the plane which passes through these vectors is also the eigenspace, right? Because it is the span of these two eigenvectors. So this entire thing can also be a an invariant subspace. Okay, we can actually see that by an example. So eigenspaces are there, so in general. So why do I say that? Let us take A times x. Okay, I can always write x equal to C1 V1 plus C2 V2, okay, where V1 and V2 are eigenvectors of A. So this is nothing but A C1 V1 plus C2 V2 is equal to C1 A V1 plus C2 A V2, that is nothing but C1 lambda 1 V1 plus C2 lambda 2 V2, correct. This is just my eigen, I just substitute that. A V1 is lambda 1 V1. Okay. So what do we have here? This is nothing but a linear combination of V1 and V2, which is again on the plane, right? So that's the that's why it's called an eigenspace. Okay. So now if you have A1 V1 equal to lambda V1 etc., AVN is equal to lambda n Vn. You can club this and write A times V is some lambda times V, correct. So this is nothing but A implies A is so it's not lambda times V, it's V times lambda. Okay. So this is V lambda V inverse. So this is my this is simply my so if you see here, this is a similarity transformation, okay, where the modal matrix is the eigenvectors. Okay. So if you choose the modal matrix as your eigenvectors, then you will get a if the A matrix is good in the sense it's not defective, in the sense you will see that what algebraic multiplicity and those things are, then you will get a diagonal system. Okay, the system becomes diagonal now in the in some coordinates. We will see what coordinates those are. So you know how to take the, I am not going to say how to take the eigenvalues, eigenvectors and all. It's just for 2 cross 2, 3 cross 3 and all you can do by hand, rest you can leave it to MATLAB. So I am not going to see how all that is done. Let us take a system x dot equal to Ax. Okay. So why are we doing this? X dot equal to Ax. Now I write x dot equal to A as V lambda V inverse. Okay. Now I take V to the other side, V inverse x dot equal to lambda V inverse x. Now I can write this as z. So I am writing z equal to V inverse x. Okay. So I can take the z dot also. Z dot is nothing but V inverse x dot. Okay. So this is nothing but z dot. So which implies z dot is, okay. So in these coordinates, my system is now diagonal. Okay. So it will be z1, z2, etc. zn is equal to lambda 1, etc. lambda n, zeros. So these are dots, sorry, z1 up to zn. So now things are easy to analyze, right? So if you can diagonalize the system, it's very easy to analyze. So you can analyze a lot of things like controllability, stability, everything. Okay. So this is why you need eigenvalue decomposition. Now the thing is, there are two parameters for each eigenvalue. One is the number of times it repeats. Okay. You would have seen repeated poles and all in your control theory. So it's related to this. We'll see why in later weeks, I think. So the algebraic multiplicity is the number of times the eigenvalue repeats. Okay. Geometric multiplicity is the dimension of the eigenspace of, say, lambda 1, eigenvalue lambda 1. Okay. So what does this mean? Let's take a system, let's take a matrix who has lambda 1, lambda 2, lambda 3, 0, 0, 0, 1, 0, 0. Okay. In this case, okay, sorry, let's make this all repeating, just a second. So this is lambda, lambda, lambda. Okay. So lambda is repeated thrice. So in this case, am is equal to 3. What is the geometric multiplicity? So geometric multiplicity, okay, before that I'll have to talk about the generalized eigenvectors, but anyways. So in this case, if you find the eigenvectors, you will see that there are only 2 eigenvectors. Okay. Maybe we can do that right now. So what is my eigenvector equation? Lambda I minus a equal to 0. Okay. So I'll write that 0, 0, 0, 0, 0 minus 1, 0, 0, 0. Okay. Times some x equal to 0. Okay. So when is this 0? So the first one is 1, 0, 0, 0, 1, 0. Okay. Then there is one more. So there are only 2 of these, right? There are only 2 vectors which can give you a 0. Okay. So which means my eigenspace is not of dimension 3. Okay. It's of a lesser dimension. So my geometric multiplicity has, these are my basis vectors for the eigenspace. Okay. So its geometric multiplicity is 2. Now what do you do about that one more vector? So yeah, so what you can do is, so these are my V1 and V2. Okay. So what you can do is a minus lambda I, okay, V1 is equal to V3 is equal to V2 or V1, it does not matter. Okay. So basically what you are trying to do is you are projecting some vector which is outside this plane onto this eigenspace. Okay. This is what it's entirely done, right, in this case. Okay. I want a vector which is getting acted on by a minus lambda I to be equal to one of these vectors. It could be a combination also, V1 plus a V2, it does not matter. Finally, you have to reach that space. Okay. So let's say you have an eigenspace like this, V1, V2. Okay. Now you want to you want to make sure a minus lambda I square is 0, because the geometric multiplicity is 2. So I have to make sure it's 0 times times V is 0. Okay. So in one step I have to reach here on this space. Okay. In next step it will be 0. So, if I take a minus lambda I times a minus lambda I times v equal to 0, I will set this as some V3. Okay. If I set that as V3, what do I want? A minus lambda I, sorry, I will set this as some combination of alpha plus. Okay. So, if I am now on this space, I know that this times, you know, this vector, whatever this vector is, this is 0. Okay. So, that is why we use generalized eigenvectors, those are called generalized eigenvectors. So, that is the logic behind why we are doing that. So, yeah, so this is nothing but now if I set that a minus lambda I times some V3 equal to this vector. Okay. So, now if you know these matrices where GM is less than AM cannot be diagonalized. Okay. So, what is the next best thing you can do? You can have a block diagonal form. Okay. So, then but next best thing is a block diagonal form. Okay. So, since you can diagonalize exactly like 0, lambda 1, you can do this. The next best thing is to block diagonalize. So, this is one block, I will call it J1, why we will see later, we will see now why, J1, J2 etc. these are blocks. Okay. Some not n, maybe some m. Okay. There are m Jordan blocks. So, this is called a Jordan canonical form or a Jordan decomposition. Okay. It is a more general form of eigenvalue decomposition. Okay. So, we will see an example. Let us take 1, 1, 2, just a second, 2, 2 and 3. Okay. I am going to put 1, 0, 1. Okay. So, that is it. So, this is a matrix and all the rest are zeros. So, in this case, what is the algebraic multiplicity of 1? Algebraic multiplicity of 1? So, this is 0. So, this. I'll write this properly. Okay. So, what do you think is the algebraic multiplicity of 1?
Is it 2?
Yeah, 2, and the geometric multiplicity is?
I believe it's 2, but I'm not sure why.
You said
I
2?
didn't get that. Yeah, I said 2, but I don't really get
Yeah, so it's actually 1.
Okay.
So, it's 1 because this is a single Jordan block. Okay. So, a number of Jordan blocks is equal to the geometric multiplicity of one eigenvalue. Okay. So, of an eigenvalue. We will see in the, we will look at an example if it is not clear. So, in this case you have two Jordan blocks, one is this and the other one is this. Okay. So, there is a 0 here, okay, never mind that. So, rest all are zeros. So, now for AM the algebraic multiplicity is pretty easy, you just have to count the number of times. So, that is 3, and the geometric multiplicity of 2 is actually 2, because is the same as dimension of eigenspace. Okay. So, yeah. So, we will see why you get a 1 there, and for the third one algebraic multiplicity of 3 is nothing but 1, and geometric multiplicity is also 1 because there is one block. Okay, so we will see why it's the case. Okay, so you have A times V1 equal to lambda times V1 and lambda 1. Okay, so so if the geometric multiplicity is 2, let's take an example where AM is equal to 2 and GM equal to 1. Okay, so which means I have just one eigenvector, and what is my second equation? A times V2 equal to V1. Sorry, A minus lambda I times V2 equals V1. Okay, this is nothing but A times V2 equal to lambda I times V2. Okay, I am just expanding that out, plus V1. Okay, so this is nothing but lambda V2 plus V1, correct. So if I write A, V1, V2, what do I get? I will get lambda 1 V1, lambda, okay, it is the same, lambda 1 V2 plus V1, correct. Now if I want to write this as a matrix form, how do I write? V1, V2, how do I write this? This is nothing but lambda 1, 0, lambda 1, 1, correct. So yep, so that's why. So now if you have I mean you can just write this over and over. So let's say we will take another example. Let's take AM algebraic multiplicity as 3. Okay, this is the case of the first one. Okay, this is the case of the first one. You got that clear, right? This part is clear, right?
Yeah.
So yeah, so this will be my block. This is called a Jordan block. So you can just check what appears here, if it's 0 or 1. Okay, you just have to check that. Now let's take the case geometric multiplicity is 2. Okay, which means there are 2 eigenvectors now. So I can write A lambda equal to lambda V1, A lambda equal to lambda V2. Oh sorry, I'm so sorry. What am I writing? V1, V2. V1, V2. Okay, that is clear. So I have 2 of them. Now I need to find the third one, because the third one is not there, it's not the basis of the eigenspace. So the third one, how will I find? A minus lambda I V, so I will call it V3 equal to V2. Okay, so this is nothing but A times V3 equal to lambda I times V3 plus V2. Okay, so this is A V3 equals lambda V3 plus V2. Okay, or it could be V1 also. Okay, so it could be V1 also, you can write it as V1 also, it does not matter. So in this case I am just writing V2. So how will I write this finally? A V1, V2, V3 is equal to A V1 is lambda V1, lambda V2, lambda V3 plus V2. So this is equal to, if you write V1, V2, V3, so these are vectors. This is nothing but lambda 1, lambda 0, 0, 0, lambda 0, sorry, it will be 1 there, just a second. Okay, maybe it's okay, I think I wrote it the other way. Okay, something I made a mistake here. Okay, I think I made a mistake when I wrote something, not sure what. Lambda times V1, lambda times V2 and then the other one should be, there should be a 1 here, so that's how it should be. Okay, there is a, okay, I think there will be a transpose here. I'll tell you why. So apparently there is a transpose here, because when we write this, you know, it's just the same way we wrote as a, you know, the basis here, right? Wait, where is that? Yeah, here we took 1 0 0 and wrote it like this, right? So again, all these decompositions are again change of basis. So essentially there will be a, you know, it's just a small numerical thing. So there will be a transpose here. That's why instead of 1 lambda, it's, you know, it's this way. Okay. So this is my matrix. Now if I want to choose the Jordan blocks, it is this one and this one. Okay. So a Jordan block will have 1 on its topmost. Okay. So there is a 1 there. Okay. Now in the third case, it's pretty straightforward. Now let's take an example where AM equal to 3, GM equal to 1. Then how will the Jordan block look? So you have AV1 equal to lambda V1, okay, AV2, sorry, A minus lambda I V2 equal to V1, okay, because there is only one vector now. Other one you have to find based on these vectors. So AV2 is equal to lambda V2 plus V1, okay, and the third one A minus lambda I V3 is equal to V2, okay, which implies AV3 equal to lambda V3 plus V2. Okay. Now if you write the block, you will get lambda, okay, 1 1 0 0 0 0. That's what you are going to get. Okay. So that's why you have these. So now how many Jordan blocks are there? Just one. This entire thing is a block. Okay. So yeah, I hope it's clear now, at least a bit. So this is my Jordan block. I'll write it as J. Okay. So it's not diagonal because the matrix is defective in some sense. It doesn't span, the eigenspace doesn't span the entire R3, so which means it's defective. Okay. So that's why. Okay. So that is done. Now we will look at look at another question. Maybe we will look at some simple question of eigenvalue eigenvectors. So I know the eigenvalue of A is equal to -1 and 5. Okay. What is the eigenvalue of A cube plus 3A square plus 2A plus 5I? How will I find this? I mean, it's pretty easy. I am just, just refreshing all these math things, because you will use this in something called the Cayley-Hamilton theorem and stuff like that. So how do you so how do you find the eigenvalue of this matrix, this entire matrix? Let's say I call it P, the eigenvalue of P. Okay, I think your mic is not okay. So yeah, to find the eigenvalue of this matrix, just plug in these two values in this polynomial and it works. So it's nothing but -1 cube plus 3 into -1 square plus 2 into -1 plus 5 into 1. Okay, this is nothing but 1 minus 3 -1 plus 3 minus 2 plus 5. So this is nothing but 5. Okay. and in the second case just plug in 5. So, that is 5 cube plus 3 into 25 plus 2 into 5 plus 5. So, this is nothing but 125 plus 75 plus 10 plus 5, which is something, which is 215. So, it is pretty straightforward on how to find eigenvalues of a polynomial equation of a matrix. Okay. Yeah, we look at second order systems. Okay. Let us take a second order matrix A, B, C, D. Okay. It is a matrix. Now, we know that lambda 1 times lambda 2 is the determinant, I will denote this as delta, and lambda 1 plus lambda 2 is the trace. Okay. Now, instead of solving the maybe you do not need the exact values of the eigenvalues, you just need to know their if they are positive or negative. So, what you can do is let us say there are all 4 combinations and there are more combinations. Okay. So, lambda 1 lambda 2 will be both are positive, means lambda 1 and lambda 2 are positive. Determinant negative means So, if you have the determinant delta and trace as tau, if both are positive, then we can say that the eigenvalues have both positive real part. Okay. And if the determinant is negative, one of them is positive, the other one is negative. Okay. And if both are negative, then so in this case also one of them is positive, other is negative. If both are negative, then we can for sure say trace and determinant both negative. Yeah, okay, sorry. I think I wrote the table wrong. That's why. Plus, just a second. Okay, so if both are positive, then I can say both my eigenvalues have positive real part. If the determinant is positive and the trace is negative, so what is the combination which will give determinant positive and trace negative, which means both should be negative, right? Both eigenvalues are negative. And in other two cases, one is positive, the other is negative. Okay. And let us take the case where determinant is 0 and trace is not 0, then which means one of them is 0, the other one is plus or minus, it could be anything. Okay. If both are 0, then there is only two cases. Okay. For a 2-dimensional system, there are only two matrices which will do that. One is 0 0 0 0, other one is 0 1 0 0. Okay. So, now you know why it is the you will see what is the difference between these two matrices actually. So, this is this 0 matrix will the system dynamics are totally different. So, so what does this mean? There are two poles at the origin, correct? If you look at this matrix and convert it to state space, you know that the eigenvalues are 0 and you have repeated two poles. This in fact is an unstable system, right? So, you will see what the significance of the AMN, the algebraic and geometric multiplicities are. Okay. So yeah, that's just for a second order system, and most of the things you will be dealing with second order, or mechanical systems are mostly second order in the sense it has position and velocity. So yeah, so you can always decouple and do a second order analysis. So yeah. Okay, now we will move on to singular value decompositions. So what we are talking about is till now are matrices that are square. Okay, before that I will just give one more thing. For symmetric matrices, the eigenvalues are real. Okay. Then what sort of matrices will you get purely imaginary eigenvalues? So if you are there, you can unmute and say. So we know that for symmetric matrices, eigenvalues are real. So what is the other end of that? Purely imaginary.
Symmetric matrices.
Yeah, so purely imaginary, right? I mean, these are purely imaginary eigenvalues. So skew symmetric matrices. I mean, 0 is a possibility, but I am not taking 0 into consideration. So skew symmetric matrices will have purely imaginary, correct? So yeah, these sort of matrices you would have come across in rotations and things like that. Okay, so these are purely imaginary. That was one thing which I wanted to say. Then we'll move on to singular value decomposition. Okay, so we were talking about only square matrices, but now let's say I am talking about any general matrix M cross N. Okay, so what are singular values? So singular values. Okay, how do I start with this? One sec. Yeah. So you know that a matrix does two things, right? One is rotation, other one is scaling. Okay. So what we are going to do is we will split this into two. Okay, matrices which only do rotations and the matrices which only do scaling. That's what singular value decomposition is all about. Okay, so you have A is equal to, you have to decompose it into U sigma V transpose or V conjugate transpose. We are only looking at real matrices, so it's just transpose. So U and V are something called unitary matrices, or they are orthogonal matrices. Okay, unitary is in the complex space. So U and V are orthogonal matrices. Okay, so which means U transpose is identity. Okay, what is the dimension? This is M cross M, this is N cross N, and sigma is M cross N. So U transpose will be identity, V transpose is also identity. Okay, and sigma will look something like this: sigma 1, sigma r, rest all are zeros. Okay, so this is your single. So these values are called singular values. Now how do we obtain them? So if you see here clearly, if A acts on a vector x, okay, where x belongs to Rn, okay, let us say y equal to Ax and y belongs to Rm. Okay, what is this actually? U sigma V transpose x. What is this doing? So you know that this is nothing but a rotation matrix, correct? Something like a rotation matrix. Okay, so V transpose x is a rotation. So this is rotation. Now I'll call it let's say V transpose x equal to x1. Okay, U sigma x1, correct? What is sigma times x1? This is nothing but scaling, because it's just scalar multiplication, correct? So it's just multiplying with a scalar, so it's scaling. I'll call it x2. Okay, now I take again the next one, U times x2. This is again a rotation, but you see the first rotation is in Rn, the second rotation is in Rm. Okay, so that's the difference. If the matrix is square, then the rotations are same. Okay, so in the same dimension, I mean. So this is equal to y. Okay, this is again a rotation. So a matrix operating on a vector can be viewed as rotation, scaling, and then again rotation. Okay, so that is the general thing. So basically, if you have some vector like this, okay, in R2 you take a vector. Okay, first it rotates in R2, let's say n equal to 2 and m equal to 3. So, first it rotates to R here, okay, I will draw it with some other color, okay, it rotates in R2, then it scales, okay, let us say my scaling is this much, it scales to this big, okay, let us say it scales according to sigma, and now it again rotates. Now rotation is in R3, correct. So, my now rotation is, let us say it rotates to some this new vector, this is my y, okay. So, I had x, x1, x2, y. So, that is what is happening for a matrix. So, we are viewing this in a, we decompose these properties of a matrix, and this decomposition is called singular value decomposition. Okay, now, why do we use singular value decomposition? Okay, first before that, how to obtain that? Okay, before that, yeah, one sec. Okay. So, before that, how do you obtain singular value decomposition? So, you have A equal to U sigma V transpose. So, A transpose is nothing but U sigma V transpose times U sigma V transpose the whole transpose. This is U sigma V transpose, okay, V sigma U transpose. I just took the transpose, okay, and sigma is a diagonal matrix. So, transpose doesn't matter. So, this is nothing but U sigma, this is identity sigma square U transpose, correct. So, if you find the eigenvalue of A transpose, eigenvalue and eigenvector is nothing but U and sigma square, okay. Now, if you want the singular values, just take the root of the sigma square, okay, that is it. So, what about V? We have to do the other way, we have to take A transpose A, this is nothing but U sigma V transpose the whole transpose times U sigma V transpose, okay. This is nothing but V sigma V sigma square V transpose, okay. So, now again do the same thing and eigenvalue. So, the eigenvectors of A transpose A is nothing but V, okay. So, that is basically your singular value decomposition. Now, where do we use this? So, first it used to be used in image processing, image compression, okay. Then you can actually show that this singular value decomposition is nothing but it is similar to Fourier transform in a signal space, in a continuous function space, okay. So, we will look at an example of image processing. Maybe I will just share my other screen, just a second. I hope my screen is visible now. Yeah. So, we look at an example from MATLAB. So, I hope the code is also legible, you can read the code.
Yeah, it's clear.
Okay. So, what I am doing is, I have an image of a deer, okay. So, I will just run this section. Just a second. Maybe I will just comment this out. Okay. Oh, okay. I'm not sure why it's taking so much time. Okay, maybe I'll just open this up and show. It's taking some time, just a second. I'll restart. Okay, I'll just restart MATLAB, just a second. Yeah. I don't know why it's taking time today. Maybe some background processes. Okay, so I'll just. Okay, so this is the image of those deers, okay, or black bucks. So, okay, so this is my image which I have. What I am doing is now I am just reading the image, I am just loading the image as A. So, what is my A matrix look like? So, A is just it's called a tensor. We are not going to look at what tensors are in this case, but it stores a 3-dimensional, it's a 3D object, not a matrices are 2D, right? Basically, you have a X and a Y, okay? Tensors are 3D. So, 391 cross 570 is my pixel size, okay? 391 cross 570 is the pixel size. Now, I convert it to a grayscale image, okay? And then I just plot it here. So, now what is the dimension of X? So, I take away the color information. So, now it's just 391 cross, I just take away the color information, sorry, it's X. Okay. So, I just take the information of RGB. Now, it's just brightness, okay, 391 cross 570, it's my pixel size, height cross width, okay. So, now what I do is I take the SVD of this matrix. So, I can just maybe print A of the first 10. If I print, so these are just values, okay. It's a bit range from 0 to 256, I think, I am not sure. So, it's from 0 to 256, okay. So, it's just numbers based on how black or how white the pixel is. So, now I take the now I take the SVD of this matrix, okay. I will take the SVD of this matrix, just comment. Now, if I take the SVD of this matrix, okay. So, now I have U. So, okay, so it's a huge matrix. Okay. So, what is the size of U? It's 391 cross 391, M cross M. Size of V, 570 cross 570. Now, what I am going to do is, I know that there are R singular values, right. So, what is the rank of S? We will see what is the rank of S, okay. Rank of S is nothing but number of non-zero diagonal entries, correct. So, it is 391, okay. There are 391 non-zero diagonal entries out of 570, okay. So, I can truncate the image to that much, 391 if I want, okay. We will see first what happens. So, if I take only the first 391 columns and rows, okay, of the SVD, basically I take the columns of U and rows of V, okay, and diagonal 391 diagonal elements of S. What will I get? So, the second image, it does not look much different, right, but now my memory and things like that are very less compared to the first case. Now, I will keep reducing this, okay. Let us take 100, first 100 columns and rows. Now, let us see what happens. Okay, nothing much, you see a bit of blurriness, but maybe if I open this up, you know it's blurred a bit. So, it's a bit blurred, see, this is what happens when you do image compression, right. So, it's a bit more blurred. Now, let us further reduce to 50. Okay. If I further reduce to 50, I mean still you can figure out it's, the pictures is about a deer, but it's the quality has gone down very low. Okay. So now if I further reduce to 20, now this is very bad, you can't deal with it. So let's take 70, okay, for our purpose, for some, let's say I'm happy with 70, I'm happy with this image compression. I'm not going to put it on a really big screen, so I'm okay with this. Okay, I'm okay with this. Now let's look at the size of the approximate. So size of x approx. So if you see here, the size doesn't change. So the number of pixels doesn't change. Okay, it's just the amount of information that changes. So singular values actually tells you the amount of information present in the matrix. Okay, and it is ordered also. So the first one will be of the highest information, or the first column in U and first row in V will have the highest information, highest weightage. Okay, and it keeps reducing, and the last are zeros, which doesn't matter if they are there or not. They are just killing away memory. Okay, so you can view SVD as you not just rotations and scaling. It's about how much information is there in each of the vectors. Okay, so you can reduce the size amount of information there, as you seen here. So if you take the first 70 vectors, then you will get a picture with less information. Okay, so that's the thing. Sometimes you can use this to reduce noise also. Okay, so is that clear, like how to do image compression using SVD? Now these days people, yeah, no, say you can.
Yeah, I got the idea of image compression, but are there any other applications of SVD? Maybe something related to lead control theory over here.
Okay, for control theory. So the thing is, in control theory, it's generally square matrices. Okay. So the thing is, okay, I'll tell you a thing in control theory. So, so there is, so let's say you don't have the system model. Okay. Maybe I'll switch it to my other screen. I'll show you. Maybe I'll switch it to other screen before that. In control theory, yes, there are uses. I'll share screen. Okay. So let's say you don't have a system model. Okay, x dot equal to ax. You don't have a model. You don't know what a is. So what do? You go for data, system identification and things like that. Let's say you collect data samples, okay, x of 0 up to x of t. You collect some data samples, okay. Now this is not square, this is n cross t, t minus 1. I will put this, now it's n cross t minus 1, sorry, t, this is t minus 1. So it's a n cross t matrix, okay. So now we have some data samples. Okay. Now I'll call this x0, this entire matrix as x0. Now I'll write, assume this is a discrete time system for the time being. It's easier for discrete time. Okay. Assume it's a discrete time system. You don't know what a is. You have, now I take one step ahead values, x1, xt. This is also n cross t. Okay. So this is nothing but a times, correct. I am just writing it in a different way. This is my system data collected using sensors and things like that. I don't know the a matrix, but I know the relation between these two. What is that? X of 1 is equal to a x of 0 and so on, correct. X of t is equal to a x of t minus 1, correct. I can write this as x1 is equal to A x naught, correct? I can just group all this up and write it like this. Now these are not square matrices. And the other thing is, this might contain unwanted information. You know, you don't need that much information to estimate A. Okay. So let's take, let's say A is just 2 cross 2. You don't need, let's say you collected thousands of samples from some process, some chemical process, something. Okay. So some process you have collected that much samples, and you are trying to estimate the system model. So how will you estimate the system model in this case? You have to take the inverse here, right? A is nothing but x1 x0 inverse, right? Some sort of an inverse, but you don't, it's not a square matrix, so you don't have an inverse. So what do? You go for something called a pseudo inverse. Okay, you would have heard of the pseudo inverse. Pseudo inverse is nothing but your, you use SVD to find the pseudo inverse actually. So x1 bar x0 pseudo inverse is represented by some sort of a dagger. Okay, so this is your A, correct? You understood till here, right? What the concept is?
Yeah, I understand.
So your A matrix is nothing but x1 x0 pseudo inverse. But how do you find pseudo inverse? This is nothing but so x0 can be written as U sigma V transpose. Okay, so this is nothing but okay. So pseudo inverse, you would have seen the formula, right? I actually forgot there are okay, just a second. Just a second. Yeah, it's nothing but A transpose A, the whole inverse. Okay, in this case it's x0 transpose x0, the whole inverse times x transpose. Okay, this is my pseudo inverse. Okay, so this is the definition of pseudo inverse for if they have linearly independent columns. Okay, and there is one version for linearly independent rows also. Now in this case, since the rank may be different, linearly independent columns and both might be different. Okay, so how do you take this? You just substitute this. What do you get? V sigma U transport U sigma V transpose. What is x naught transpose? V sigma U transpose. Correct. So what is this identity? V sigma square V transpose times V sigma U transpose. Correct. What is this equal to? V. Okay, there is an inverse here. You can take the inverse of this matrix. What is the inverse of that matrix? V sigma square inverse V transpose, because now because V and V transpose are orthogonal, you can take the inverse very easily here, right? Okay, because V inverse is nothing but V transpose. This is same as taking the inverse only for the diagonal term times V sigma U transpose. What is this equal to? This is again identity. Basically I am just doing algebraic steps, that's why I am going fast. If you want, you can again stop me and ask. So this is nothing but sigma square. So this is nothing but sigma inverse U transpose. So that is my pseudo inverse. Okay. So now how do I find the pseudo inverse? So how do I find the A matrix? V sigma inverse U transpose. Okay. So that's my A matrix now. Just using data. Okay. So if I want to estimate the state matrix from data, it's in estimation theory, you can use this. Now the thing is, the sensor data might have unnecessary information which we don't need to estimate. So what do? Just like your image compression, you only take the top R values. You take the first 50. So I hope, is that clear or?
Yeah, makes sense.
So yeah, so if when you want to estimate the system dynamics and all, you will use data to find the something like this to identify the system matrices. So that's why you use this in control theory. So yeah, so do you have any other doubts or? Do you have any more questions? Yeah.
I don't have any other question right now.
Okay, so maybe then we can meet next week, and happy Independence Day, by the way. So yeah,
Yeah, same thing.
yeah, yeah. So yeah, we'll meet next week then. Okay,
Yeah, thank you.
cool. Yeah, thank you.